Today we are tasked with finding the volume when the area between these two curves is revolved around the x-axis. I've already gone ahead and used a graphing utility, a particularly good one, which can be found online, and I will put a link in the description for you to fool around with as well. I've enlisted the help of some visual aids to try and demonstrate to you exactly what volume we are talking about, for hints on how to generate these kinds of pictures by hand. Stay tuned, I'll try and make a tutorial video on that at some point. But once we understand that this is the volume we're talking about and that these are the boundaries of interest that bind that volume between these two curves, what I'd like to do is show you how the formula is arrived at for calculating this volume. It basically starts with the idea that we can take blue space, the volume represented by the outermost function, that one is the curved parabolic function, and if we subtract the purple space, which would be blank space, like is represented here in the three-dimensional graph, you have your answer. This is called the washer method, because what you get when you subtract my blue space from my purple space is a washer that fills in the space from here to here. The volume of the blue space is thought about in terms of a summation of disks that stack up to make that blue space. I usually like to talk about the volume of a singular disk. You might notice that this disk is cylindrical. The volume of a cylinder is pi r squared h. But in terms of our disk, we notice that we have a height given by an infinitesimally small unit of length on the x-axis. You might notice that our radius is given by the height of this function above the x-axis, which is of course the function itself. Now the blue function, the outermost function, the upper one, is represented by this formula. So r will be equal to 6 minus 2x minus x squared in general. So that's enough for us to conclude that the volume of the disk I've drawn here, the arbitrary one that represents any point within the area of interest, is pi 6 minus 2x minus x squared squared delta x. What we'd like to do is stack up all the disks of interest, all the ones that start from this side of the area and go all the way up to the end of it. So it would be sensible to say that the volume of all the disks, the volume of the disks, plural, is a summation of some kind of pi 6 minus 2x's, x squareds, and delta x's. Of course, in calculus, we don't use summation notation that much. Instead, we use integrals. We can do the integral from -3 to 0, pi 6 minus 2x minus x squared dx. In calculus terms, the small delta x represented here is expressed with a dx. It becomes truly infinitesimal. This represents a number. Hold that thought while we figure out what we're going to subtract from that number, while we figure out the dimensions of the purple space, or the void space, as given by this picture. The volume of the purple disks I've drawn is also given by pi r squared h, the definition. But this time, the radius is a little bit smaller. It's given by the line y equals x plus 6. So the radius is represented by x plus 6 squared. The height, so to speak, is once again a delta x. For similar reasons as the previous example, the volume of all my purple disks, plural, will be the integral from -3 to 0 of pi x plus 6 squared dx. The total area that we're interested in will be the volume of the blue minus the volume of the purple, or the integral from -3 to 0 of pi 6 minus 2x minus x squared dx minus the integral from -3 to 0 of pi x plus 6 squared dx. Because of the rules of sums and differences of integrals, as well as the ability to factor out a pi out of here, it becomes pi integral from -3 to 0 of 6 minus 2x minus x squared minus x plus 6 squared dx. The value of this integral, when properly evaluated, is 152.66 or so. That is the answer to the volume of this solid. But more interesting is the fact that the result can be generalized. In general, the volume of an area bounded by two curves is given by pi integral from a to b of f of x squared minus g of x squared dx. F of x and g of x will represent the radius of the upper and lower curve respectively, and a to b requires some figuring out. You may or may not have access to a visual aid depending on to a graphing utility depending on what kind of class you're taking. Here I kind of started off with that knowledge, but at some point I will post a video demonstrating how to arrive at these sorts of limits yourself. But in general, this formula will get you where you need to be.